Okay. Okay. Um, so there's a bunch of things. Today's the agenda specifically is that you want this now. Yes, probably. Yeah. So the agenda would be mostly first part would be whatever questions you have. I read some of the LLM workflow reviews. There were some questions. You can bring them up if you can actually look up the PSR and bring them up as we. I can answer them, and we can discuss that. And there's also 2 LLM planning summer school lectures that you're supposed to actually watch in lieu of last class that I missed. About 7 of you watched, and 4 of you actually posted. So not anybody, but I mean, again, as I said, I'm not going to handhold. It's a graduate class, so if you don't do it, you don't do it. Basically, there were 2 full lectures essentially there, and that's about stuff that you probably care about, which is how to use the LLMs. But you have to look at those lectures and post your questions. I think there are only 4 people who posted questions. I'm not sure. I think I'm not being sufficiently menacing that people are actually taking it easily, but we are supposed to do that. Anyway, so if there are any questions on that too, I'll do that. And then the topic that I'm going to discuss today, the specific topic, the second topic that I'm going to discuss today is temporal planning, which is basically, okay. So basically, what happens when actions, in classical planning that we have looked at until now, basically actions are instantaneous, right? So it's like a point. There's a before and an after for each of the points. But in real world, in general, there's lots and lots of things. Classical planning is an abstraction. In real world, one of the things that is actually true of actions is they have duration. So the action starts and it goes on for a while and ends. And the effects of the actions can come anywhere during the action. It may be coming at the very end, it may be coming in the beginning, it may be coming in the middle. Similarly, the action might require preconditions at different places too, the beginning or middle or the end. And if you have that, so it's still a deterministic planning problem in the sense that the dynamics of the environment are still deterministic, but the actions are now durative. And it will be very interesting to see how what you learned about classical planning will generalize to temporal planning. Okay, and there are other things that we'll talk about. But actually, that's decided that I'll pick up the temporal planning earlier because, first of all, it is actually as close to classical as possible because it's still the deterministic thing, except that you now have actions with durations. And secondly, most of all these agentic system stuff basically requires actions with durations. And so basically people are ignoring them. And so it's worthwhile understanding what is the right way to do it before you know what you actually get done. So that's at least what I am planning to do. And the other thing actually related to that, I forgot to write the question. One of the other things about the questions is if you have any questions about the semester project, I understand that a whole bunch of things happened in the last week because I sent a mail about projects, semester projects. I had my students come and present what they're working on so that you might get some ideas about what sorts of projects you're looking at. And then I also gave like a deadline for generating, basically saying whether you're doing type 1 or type 2 projects and then give some description of it. And so if you have any questions on that, since I only sent the mail and I didn't actually show up for the class after that, if you have any questions on that, those are also fair game for today. Okay, so that's basically the agenda. So anyway, as I told you, I was away in India. That was a, like a panel I was a part of in AI Impact Summit in India. These are tons and tons of people. Actually, you can't see it, but I mean, there are lots and lots of people there. Actually, there were 300,000 people apparently who showed up during to this thing. Everything in India is big, and then per day about 70,000 people showed up. But this one is probably like 700, 800 people on that auditorium. Okay, there was some fun stuff about this. Is basically research directions symposium and a panel that I was part of, and there was some question about AGI, and I had some funny answer. Then, if you are interested, I kind of tweeted some excerpts of what I was saying there on my Twitter. You can actually look them up. I also did other things that, since you go all the way to Delhi, actually. So this actually happens to be for the non-Indians. What is it? What non-Indians would not know that it's what or. So anyway, it's not. It looks kind of like sort of like Taj Mahal, but it's because it's one of the prototypes for Taj Mahal, and this is called Humayun's tomb. Humayun was the father of the guy. Humayun is the father of Akbar, and Akbar's son is Shah Jahan. Shah Jahan basically built Taj Mahal for Mumtaz Mahal. Anyway, so to give you a sense, that's the difference in the two things. That's actually Taj Mahal. This guy, and the same week, this guy is the new ambassador from US to India. And when he showed up, if you go to Taj Mahal, you'll never get a picture like this. Basically, in India, there is this whole thing called VIP culture. And he's VVIP. I'm a small VIP, but he was VVIP. And so they basically stopped everyone from coming to Taj Mahal that day, cleaned it up, just so that he could have a picture taken. I mean, I thought the whole point of AI was you could do this without introducing people. You can just put him in front of it, but anyway. So you can see the idea, actually. I mean, anybody from Turkey here? Turkish origin here in the class? Actually, the whole Islamic architecture of this type starts from Istanbul in Turkey. So if you read to Istanbul, you would see things like Blue Mosque and Suleimani Mosque. And the guy who was building those, essentially his disciples then came and started building in India during the Mughal architecture. So anyway, that's about that. And so the thing interesting about it is this freestanding huge dome is like very surprising about Taj Mahal. And if you go to Blue Mosque, which is the very beginning of this kind of architecture, you'll see if you go inside, there are like tons and tons of pillars. So there is no free space because the pillars have to hold the thing from falling. And what happened from then to Taj Mahal is if you go inside, it's like basically a free space. So they figured out how to make this without actually having to put too many pillars. That clutters up the environment. So that clutters up the space. Anyway, so that's that. Like I said, I was a VIP, not a VVIP. So somebody came and picked me up. And unfortunately, I was supposed to go to the Prime Minister's dinner. I even had apparently a table, as you can see, but they didn't send me the email. That's extremely important to actually get in. It's a highly, very, very high security event. So I didn't know that I didn't get the email, so I assumed I wasn't going. But then a friend of mine who did go found that there was actually a place with my name. And unfortunately, I was supposed to be sitting with Raj Reddy, who is one of the Turing Award winners of AI and also AI presidents and so on. Anyway, so that was that. So of course, I kind of said that my VIP treatment is not going well. And since there was actually an article about this, in multiple newspapers, because they were apparently sick and tired of just writing about AI, so they started writing about other people complaining about their VIP treatment. So that's that. So anyway, that's my life in quick summary. And of course, I came back and I fell sick, and so I'm actually just recovering. So this would be probably the lowest energy class in this semester. So if you fall off, basically you're done. You can go home, and then we'll meet in the next class. But we'll see how it goes. Okay, so that's basically the thing. So let's go talk about any questions you have about LLM modulo or any of the lectures that you've seen. Yes?
I had a question. I know you mentioned with the critics and verifiers, you can have a learned one. How exactly does that work? Not like with a learned critic, if it's not 100% accurate, kind of defeats the point. So.
Yeah. So the point basically is, that's actually a very good question. And in general, so that the question is about learned versus guaranteed critics. So the point that I was making in that LLM modulo is, if you take the same LLM that was supposed to generate, let's say the plan, and you ask it to verify the plan, then it's not guaranteed. It's likely not to be any better at verifying its results than it is at generating. You understand what I'm saying? So because the verifier is supposed to be giving direction to the generator, and if both are blind, it's like blind leading the blind. Okay. So the only point, and in fact, there was a paper that I think in the lectures I mentioned this, but I could make, there's a paper in iClear last year, which basically show that if you actually make the LLM verify its own result, and then basically stop only when it is actually correct or something, as against just guessing once, then you would assume that its performance should improve, but it actually can worsen, because it could, in some cases, it could have generated the correct solution, but the verifier says it's incorrect. And so it just continues, and then ends up with a solution that's actually incorrect. So that's possible, okay? So now, that is not a problem if you have external guaranteed critics. Okay, the learned critique essentially is, you actually make the learning of the critique itself a sub-problem. So in the sense that you could actually, instead of just saying the LLM itself can verify, the same LLM can verify, the same LLM that's generating the plan is going to also verify the correctness. All we are saying is, imagine you have, first of all, so this basically, any learned critique is probabilistically correct critique. Right? Because essentially, you could have generated, for example, you could have given it enough number of examples of correct versus incorrect plans, and then essentially train it to kind of check which one, to kind of label the correct versus incorrect plans. And if you have shown it enough examples of that kind, then it's likely to improve its accuracy. And you can actually put some bounds on that. That's the usual point about learning. Right? So all we were saying essentially is, if you do not have in the let's see actually let me see if I can get that one. Yeah. So basically, this is the picture that you're talking about, right? So these critiques can be external critiques. They can even be LLMs, but if it's LLMs, then they're really good for style, is what I was saying. And they can be learned critiques, and if you're learned critiques, the learning can essentially be a separate process altogether. And then you learn the critique, and then you are applying it. You learn it once, and then you can apply it multiple times. That's the basic idea. There is actually a paper that we have in 2023 ICML, where there's this undergrad student I was working with, not from here, who happened to actually do this following thing, where he would take, so in general, the one way, if you're learning the critique, first of all, you can learn critiques in multiple different ways. Basically, if you have data about this is the correct plan, this is the incorrect plan, this is the correct transition, this is the incorrect transition, imagine, okay? And you give enough of those examples, you can take any classical learning technique to get a classifier. And that classifier takes as input, the plan and the artifact, and it gives out a label saying yes or no. Okay. So the question, of course, is where is the training data coming from, right? So you are supposed to have done it separately. So in this one paper, we actually did the following thing. Imagine you have fine-tuning data. So basically, if you have an LLM, you can fine-tune it with, let's say, k correct plans in blocks world, let's say, so that it generate more correct plans in blocks world, kind of. I mean, fine-tuning is not a great idea at all. I mean, I think I make jokes about, probably make jokes about it here too, which is, it's not clear whether it generalizes enough. You're spending a lot of time, training, generalizing the generators, training the generator, and it will do well in that distribution, but if it's a larger plan or a different domain, it may not do well. But be that as it may, if you're anyway doing fine-tuning, so you currently have k correct plans, and in particular, what we were looking at in that particular case is actually we were looking at actually not correct planning, but correct projection. That means if I give you a state and an action, you should give me what the new state would be, right? And in that paper, basically what we and so you can take the plans are basically giving you the state, action, state, right? And if you have this is all correct. And you can also say that if you have this state and this action, anything other than S double dash that's not equal to S dash, you can kind of assume heuristically that that's the wrong transition. Okay, so in general, actually, one of the interesting things is checking correctness is a discriminative classification task as against generative. You guys know the difference between discriminative versus generative machine learning. So checking correctness is basically, just discriminative. So basically the idea actually, by the way, it's useful thing to know that Pyx equal to Pyx Px. Right? And if you learn this, you're doing generative learning. If you just learn this, then you're doing discriminative. Right? Okay. And so the discriminative learning is more sample efficient. So the way you can do it is basically, if I give you a correct transition, then every other transition with respect to the same state and the same action, I can just assume as incorrect. Not strictly true, but you would be reasonably, And you do this, and then you can actually have a bunch of data now. So instead of just having k transitions before, and k transition sequence before, you have a lot more examples, positive as well as negative. And then you can train any learner. In that particular case, we just trained the underlying LLM itself to be a verifier. So you have two copies of the LLM. One will be a verifier copy, one will be a generator copy. And that would be a learned verifier. And we can actually show that it improves performance. But in general, learning verifiers, basically, in many cases, you only have learned verifiers. And then are probabilistic verifiers. Probabilistic verifiers are to some extent learned verifiers. Okay, so that's what I had in mind in talking about the fact that these verifiers can be, some of them can be learned verifiers. There was a question.
Are learned verifiers consistent?
Meaning what?
Like, as you said that, so basically the goal of a verifier is to verify only on the domain, or like we are going to test capabilities of LLMs like in generalization. So our verifiers also should be like trained on a generalized data as
So
well.
again, so anytime you do, so the interesting thing about external verifiers would be they would basically work for any length plan. You think in terms of plan, right? So the way, let's for example talk about what is a verifier for planning problems. You know, what is a verifier for planning problems? It turns out it was, you know, kind of, it was sort of indirectly pointed out there, but it takes there is a verifier called val, which takes as input a domain model and I and G, okay, and a plan, and says yes, no. That's it. Right? And you know how to do this, right? Because you talked about, if I can give you, the domain model is basically what? PDDL model. That means actions with preconditions and effects. And you have ING. And you gave the plan. Plan is basically a sequence of actions. If I give you a sequence of actions and say this sequence of actions solves this problem under this domain model, you can check that using progression or regression or plan space verification. Val implements basically just the progression. Do you understand what I'm saying? Now, this will work for no matter what the length of the plan is. That's the advantage. Actually, it's an interesting question whether you, I don't know whether you meant it that way or not, but it's an interesting question in the sense these kinds of classical verifiers have generalization quote unquote built in. That means they will take any length plan, any domain model, any problem, and will tell you whether the problem, the plan solves the problem. Learned ones, the one that I was talking about here, for example, certainly will not have those kinds of guarantees at all. They might be better for this particular distribution of box world problems, but may not be good at any other domain. You see what I'm saying? So these are basically, these learned ones would be like projections of this for sub cases, essentially. And this one, of course, this basically comes from our understanding of how to actually, you know, verify plans. Okay, and equivalently, if you have programs, right? So if you are doing coding with LLM modulo, then you have Python interpreter. You have a Python code, right? I mean, actually, I should call it an interpreter. Python code, unit tests. Unit tests basically say, if this is the input, the code should produce this output. Okay, and the advantage of Python interpreter is it can take any arbitrary Python code, just like Python code here, just like this plan here, which could have been generated by an LLM, here the Python code is generated by an LLM. And you have to give unit tests here, similarly, you have to give domain model in plan. You see what I'm saying? And if the unit tests are satisfied, if they fail, then you know the code is incorrect. If they succeed, that means it's probably correct, because it's all, the unit test may not cover all possible cases. So that's what is meant by partial verification. Because if your code satisfies all the unit tests, that only means that, well, those unit tests, it's working on those tests. You know, what if, you know, there are other cases that haven't actually, you know, the unit test writer didn't consider the corner cases. Okay. And so one of the other things, you know, in terms of the val kind of a model, one of the interesting questions would be who gives this domain model? Who gives this domain model? Right? Actually, to make it the same, so there is just to have. So, but then the unit tests are further spec already, essentially. So the IG is the initial goal state, and that's the spec of the problem. So you have to be giving unit tests in the Python case, in the code case. In the case of planning, you have to give the domain model. And that is where we talk about the fact that you can also get the domain model out of LLM by just asking it what are the potential preconditions and effects of actions, and then put a separate recursive LLM modulo loop where the guest model is checked either by human or some partial verification techniques. And that will give you like a model, at which point then it is fed into this val, and then it will tell you whether the plan is correct. And for this class, the advantage is that you know that this is possible. For classical planning, you have validators. And the validators work with the domain model and the initial goal state, and then check whether the plan actually goes from the initial state to the goal state. That's, if you didn't learn this, then you missed the whole semester up until now. Because that was much of what we did here. And that's what you're tracing in the second one. Yes?
On the same vein as what you were talking about with the LM getting the PDL, in the summer school lectures, we were talking about Lynn's paper about where he used the LM to
That's the one, domain model,
yeah.
ones, yeah.
But my point is this, that without putting a human in the loop, how do you actually know if the PDL is faithful to the model that you're
No, you have to have human in the loop. Or you have to have some environment directly there. So, I mean, the picture for, I don't know whether the Lynn's thing was there in these slides or not, but essentially, original way that Lin Guan paper was written was it reduces the effort needed. Previously, who was making the domain models? Previously, humans were writing the domain models. Now, humans can do less amount of work because a model will be generated and humans only have to check partially certain parts. But you cannot remove the human from the equation. That was the point. That was the point in Guan paper. Okay? Any other questions? Yes.
When you just said that when we are trying to extract planning model from PDDL and we can't remove human from the loop completely, what about these approaches that learn from demonstrations? Like some of the
Yeah, but I mean, my question has always been that I think that, so you are talking about, actually, I mean, you're talking about, there's a set of methods which say if you give whole bunch of correct plans, so the demonstrations, and you will outcomes a model, and the learner learns the model from that. Right? My opinion is that most of that work is bogus. It's been done, we wrote papers on that too. But you have to ask yourself, if in fact writing this model is so hard for you, that humans are finding it so hard to write the models, where exactly are these humans who are then actually generating many, many of these plans? Right? In fact, most of the time, if you look at the papers of that, in the planning literature, they would start with the model, use FF to generate lots of plans, then use their learning algorithm to reverse engineer the model. That makes no sense. Right? The whole idea is you shouldn't have, I mean, again, it's been said that all research is a solution looking for a problem. It's a cynical way of saying it. It's a solution. I have a solution. Hopefully, somebody can use this. And this is a kind of looks like a nice thing because if you have planned trajectories, how do you get a planning domain model out of it? But most of the time, the way they actually wind up doing it is these trajectories come from where? You know, there may be scenarios where actually, so my point is, for something like block code, etc., who are the ones who are generating these trajectories? And can you make a good argument that will be easier for them to show 10,000 or even a million trajectories than to write 15 actions? That's my sense. But you know, as far as the technique is concerned, basically, you can then take these trajectories and then, you know, kind of induce a model of it.
So the only benefit that this might have, depending on the approach that is used for learning, is that they will have someness with respect to the demonstrations that they are having, and this is not a guarantee that we can have it.
No, but first of all, general learning techniques would never do that anyway. I mean, unless you have very specific type of learning techniques. If you have a whole bunch of these, you know, for it to be, I mean, first of all, again, as I said, I have papers on this stuff too. And this is, you know, predates whole LLM stuff. It's in planning literature in general. How do you get models, you know, and so let's just make a problem where you have the plans and you can induce the model out of the plans. Okay, now for it to be interesting, actually you should consider situations where the models are actually, I'm sorry, the plans are actually noisy. And in most learning techniques, whether they're noisy or not, there is no soundness guarantees that a learning techniques, I mean, an inductive learning technique doesn't provide a soundness guarantee that the model is capturing all training data, for example. Because training error also can be non-zero. And in fact, training error should be non-zero if you have noise in the data. Actually, since you brought this up, there is a 2016 paper that we wrote, which actually predated the LLM stuff, where essentially we didn't bother trying to learn a PDL model. Instead, you learn an internal latent model which will be used to generate other plans or to verify plans. And so they basically, you take these sequences essentially and think of these plans equal to sentences in action space. I mean, actions are the words. A plan is nothing but a sentence written over actions. Actions are the words, and you know, you put a sequence of actions and you become a plan. Right? Any sequence generalization model, LLMs are one, but we were actually using a different earlier ones. So you can do a sequence generalization model on this. It will actually develop an internal model of what should come after this particular set of sequence of actions. That would be a way of actually getting a model. So it doesn't have to be the case that model means only PDL. In this class, we are obviously a lot more interested in PDL models, and in fact, Val basically assumes PDL. But the learned verifiers don't have that. Okay? Yes?
When I was watching this in the Zoom, as you were explaining this, I was thinking of this recent thing that Andrej wrote about the council of LLMs, where multiple LLMs come up with a plan, then they all vote on which LLM is the best LLM, and then the outcomes. It sounded similar to this, but it's actually LLMs critiquing.
Yes. Yeah. No, but first of all, so the test time scaling techniques typically, so if you look at this lecture, this is the slide was there too, basically. So one way to increase the correctness guarantees of a Q generator, which is LLM, do something more than just guess. Right? To me, the way to do it would be have a verifier and actually check if your Q generator is correct. The earlier methods were much simpler, honestly, which is basically, essentially make 15 guesses and take the majority guess, especially if it's a discrete space of alternatives. Suppose it's a multiple choice question and it's A, B, C, D, E are the answers. You'll ask LLM multiple times, what's the answer, what's the answer, what's the answer? And if it gives, after 15 times, it says A 10 times and B, C, D, E the other 5 times, then A wins. Right? This is called quote unquote self-consistency. It's a poor man's way of getting a little bit more out of the guess. Instead of one guess, if you are repeatedly going towards the same guess, then maybe it has higher chance or something. Okay, so that's basically self-consistency kind of ideas. But it's much what I was pushing for essentially in that talk and also in the class is actually what you want is a verifier. And it's the verifier part that actually generalizes. Because if you think of what happens in the RLVR, which is the second lecture of those 2 lectures, RLVR essentially is verified reward, RL with verified reward. And where is the verified reward coming from? Verifier is giving the reward. Is what I'm saying. So in fact, I would argue that pretty much all the reasoning models work only in domains where there are verifiers. Either the learned verifiers or the classical verifiers. It's not surprisingly, math is one of the places where reasoning models work well. Right? Because there's a clean understanding of what is correct versus what's not. Okay, and then in some sense what we're doing is you are compiling that into the generator. So you are generating many problems, trying to find solutions for them with this verifier-based technique. And then you have the problem and the solution where you can fine tune. And that's basically what post-training is. That's a way of thinking of post-training. Okay. As for the council of LLMs idea, it's in general, I'm not completely sure that council of LLMs idea makes sense. There are tons and tons of papers, but then that's this class, right? Mostly, if I just told you this one has this paper, this one has this paper, that's some other class where I just assume that because it's published, then I should just tell you. You take this class for the opinions, essentially, in addition to the papers. And then you can decide to remove the opinions. If not, otherwise you can read the papers yourself. Why do you come here? So my question about this council of LLMs nonsense is, first of all, you can just have one LLM that can do multiple guesses, and that is a council already. And there is no real difference in having multiple quote-unquote LLMs. There's just no point in having multiple copies of LLMs unless you're somehow trying to kind of, I have Claude, I have one. There's some weird reason why you wound up putting. If in general, as I said, this idea of council of gods also doesn't make sense. If you have an all-powerful god, then all-powerful god doesn't need some more gods to help the god. And if you have an all-powerful LLM, why does it need other LLMs? Unless these LLMs are like somehow specialized or something, council part doesn't make any sense to me. And in fact, this whole council of LLMs idea has been rediscovered in multiple of these agentic, multi-agent LLM frameworks. And to me, it's very questionable. I think they can all be they just become part of the database of history. Basically, a single LLM can do it. Okay.
I think they justify it by saying that one LLM is Gemini, so it's been trained by a different company, and then one is GPT.
That's what I'm saying. Then basically it is transient.
Right.
It's transient. It's like, again, I come from India where we have gods for every different thing. right? I mean, these monotheistic religions has one powerful God, right? So there is no council of Christian gods. There is only one Christian God. Okay. There is no council of Muslim gods. There is just one Muslim God. On the other hand, India is full of gods, and each of them are specialized in different things. And in fact, in my mother-in-law, for example, if she misplaces something, she specifically, there's a god who actually is in charge of finding the misplaced things. And that guy turns out to be a Muslim god. She's Hindu, but that's a Muslim god. In Hinduism, we just use all gods. So Gemini, Claude, and this Hazrat Nizmuddin or somebody else. And that's like a transient thing. If you are into imagining gods, you might as well imagine like the most all-powerful God. Right? And then in which case then they don't need any more. You see what I'm saying? Actually, I can't help but remember this funny anecdote, which might stick with you, that one time John F. Kennedy, when he was a president, there was a year that there was a bumper crop of American Nobel Prize winners. And so, because the president, he called all of them to dinner at the White House. And then he basically has to make some remarks, and he said, look, I think I cannot imagine any other time, this Roosevelt room or something where they were having dinner, had this much concentration of brain power at the same time, with the possible exception of Jefferson having dinner by himself. Did you get that? I don't know if you didn't get it. Mr. Jefferson, he's basically saying Jefferson by himself is smart enough compared to pretty much 18 or 19 Nobel Prize winners. That's a lovely way of putting things. But in general, if you have a powerful God, why do you need more gods? And if you have a powerful LLM, why do you need more LLMs? And essentially, this council of LLMs becomes some sort of a self-consistency. And it doesn't have any more theoretical guarantees. Okay? Yeah.
One thing though, but isn't it true though that when you do compare a single LLM to a series of LLMs that are orchestrated together to solve a task?
What?
Say that I have like for a like terminal use, I have to basically operate the LLMs have to go ahead and operate a terminal or basically a computer use interface. If I get a single LLM to do it, it can barely get very far with operating and getting through the computer. If I orchestrate a couple of LLMs to do so, where one LLM is responsible for spinning up higher level plans, one LLM is then specialized.
All I'm saying is that sort of view is inconsistent with the view that LLMs are general purpose to begin with. So it would make quite significant sense if you thought you have the one specialized reasoner for, let's say, motion planning, one specialized reasoner for task planning, one specialized reasoner for something else, and they all have to work together. That's very reasonable. But LLMs by definition are supposedly, I mean, especially the frontier models are supposedly very good at everything. In which case, essentially the idea that you need, one thing which does this, one thing which does other thing, is harder for me to see as a defining principle that will stay relevant for long enough time. You can write papers like that, is my point. I mean, but the question is, it's like, again, I'm also of the opinion that there's one entire area called SLMs, small language models. And my cynical view is affirmative action for academics. Because they can't train large language models. They want to write papers and they want to say small language models. It makes no sense, honestly. Right? I mean, why exactly are we doing this? You have to ask yourself. I mean, you can do things. I mean, with my sense is I want to understand, I want to think of what's the half-life period of a research direction in general. It's not that, a research direction, like in a commercial sense, if for like next 15 days, this particular kind of technique will be very helpful, after that you'll be dead, you can still become a zillionaire in the next 15 days. But from a research perspective, why maybe you're not, basically you might as well think of things that are something which have a longer horizon. Okay, and so it's an interesting question whether, is there a real reason for SLMs other than that we wish we could train large language models, but we are not Anthropic and we are not OpenAI, and so we'll say SLMs are better. And you start making up other stuff like warm and fuzzy stuff, like they are like more environmentally friendly. It's like those guys are anyway doing the large language model, so they're already taking care of killing the environment. So you're just adding a little smaller language model stuff too. But anyway, that's a separate extra opinion on some small language models. Other questions? Okay.
Wait, so are there any at all practical benefits or uses of playing around with SLMs?
I mean, in the sense that, people can start talking about the way they talk about these is things like on the edge devices, you can put a small language model, and the influence might be cheaper, etc. Again, I think it's a moving topic. And actually, you can do large language model inference is already being done on the edge devices to some extent. Again, I think, I think SLMs as a way of understanding LLMs, great. Fruit flies, as a way of understanding mammals, great. Other than who cares about fruit flies? You see what I'm saying? And this is idea called model organism studies. The reason fruit flies are interesting is because to some extent, understanding genetics of fruit flies gives you insight into the genetics of mammals, because the same fundamental principles exist across. Right? It's not that, mammals are, it's hard to get lots of mammals for, labor at home. So we're going to get tons and tons of fruit flies working together to do building of the house. That is a, bogus argument. Okay. That is that right. Other questions? Yeah.
So like, as you said, fruit flies might not have some features which are important to mammals, which need to be studied, right? Like in SLMs and LLMs, there might be some features which are not in
What are
SLM,
those?
but-
What are those? There are no, the point about evolution is that essentially, if you understand genetic basis, then everything else just comes out of it. So, I'm not quite sure what you mean. What are you trying to, what's your bigger point?
So SLMs are like we cannot, if we are trying to generalize with LLMs, then we cannot experiment with SLMs and try to prove it that hey, LLMs are generalizable, right?
No. So this is like basically saying that I will not, no, you already are alive because people did experiments with fruit flies and figured out how humans work to some extent. You understand what I'm saying? Because the drug development, etc., are done with the understanding that we develop over the fruit flies and then followed by the primates, followed by us. You see what I'm saying? It was extremely useful. It's not like saying, I want drugs only for me, no actual ideas from fruit flies for me, please. And that doesn't make any sense. Right? So there's always a question as to what parts of things that are true in SLMs will generalize to LLMs and what not. But that's fine. But at least this is the way you can actually, one of the issues for LLMs is that they're complex enough that separating out the various factors that influence the performance is extremely hard. One of the recent papers, for example, points out, I actually tweeted about this, is that, in fact, do you guys know which is the only LLM that gives out its training data? What? DeepSeek gives out the training data? What word are you guys? What? No.
Olmo?
Who said Olmo? Yes. Only Olmo gives. If your whole performance is based on the memory, which is the training data, and you say, I won't tell you my training data, then how the heck do I know whether you are actually memorizing or you are actually solving? I can't. Do you understand what I'm saying? You have no idea. No idea. When somebody says a system, an LLM is open, it just means the weights are open. That's it. Not the data. You have no idea what data they're training on. The only exception is Olmo. It's actually open because they actually give out the exact data on which they train their model. And so there's a paper last week which actually checks something that I always wanted to check, which is how much of the solutions that you are actually giving out are already present in the data. Because, in fact, this was the interesting thing, right? Because one of the original thing for Palm, I believe, right? Palm was one of the original Google LLMs. When Palm came out, one of the big things was you can ask it to explain a joke and it'll explain it. Ooh, my God, LLMs can actually do it. Now nobody cares about it, but at that time it was really impressive. The reason this is impressive is because you think that it was not trained on joke explanation and just somehow magically picked up joke explanation. But if you know anything about internet, there is internet for everybody, including human impaired. And there is a site which explains all the jokes for the people who don't understand the jokes. And that site was part of the training data. All of us think we know internet, but you have no idea what's on the internet. Do you see what I'm saying? So every possible thing could potentially be on the internet. And it's basically, this is the point I make, that you are impressed because it's not known to you, but it's known to the humanity. Because it's known to the humanity, it's on the internet. And because it's the internet, it's part of the training data. It's useful for you to know what the humanity knows right on when you need it to know. That's a very useful thing, and that's what LLMs are amazingly good at. Pretty much. Right? But on the other hand, assuming that anything that you didn't know, it makes us, oh my God, you just reason it out of first principles makes no sense. So to be actually able to check whether something is present in the training data or not, you need to have the training data available. So Olmo does, and so this new paper basically looks at things like zebra logic is one of the popular benchmarks. And they point out that 50% of the zebra logic problems are directly present in the training data, in the Olmo. You understand what I'm saying? Okay? So it's not, again, it's not, if you are looking at LLMs as, I will generate all possible data and then I'll collect all the data and somehow compress it and then put it in this thing so that anybody can access it. And there is cross connections that it's able to do. That's a useful thing. If you view it that way, it's great. If on the other hand you think, oh, I didn't know this, so you must have learned it from somewhere. No, you didn't learn it from somewhere. It basically was there in the training data. And which is exactly why I find it extremely ironic that Anthropic now says that, oh my God, Chinese are doing distillation attacks on our models. You did a distillation attack on humanity. Right? Everything we wrote for ourselves, LLMs just basically distilled it. And now you're going to complain that 150,000 lines of your, thing somebody copied over. That's like a big deal. Why am I supposed to care? Right? I mean, in fact, all of you know that pretty much. In fact, there was an article that I tweeted, but other people know that all of these guys essentially got every possible piece of data, even the stuff that's not actually on the internet, such as they bought. I mean, there's a Washington Post article that I showed called Project Panama, where they got like a zillion books, basically, and they had like a huge factory where these books are automatically, basically the spine is broken. It's the pages are copied and then OCR'd, so now it's on the internet, quote unquote. Now it becomes a training data, and then they destroy the books, right? And that's not distillation attack. It is distillation attack on the humanity, right? And so basically, this is more or less what happens in the training data of all these models. And so you have to be at least questioning, is it that it just came out of nowhere, or is it that this stuff is known to somebody? And and then it's basically, so if you would think that it's basically, there's this notion of approximate retrieval that I mentioned, I think at some point of time. So this is data, and this is reasoning. This is like retrieval, right? Retrieval from data. And this is reasoning, quote unquote. And if you are going epsilon away from retrieval of data, then you may have something like, I guess you can call it approximate retrieval. It's somewhere between pure reasoning and just essentially putting together pieces in the data that you already have been trained on. And for a vast enough data, a small generalization, a very small generalization from the data itself might be very impressive for most of you, because you have no idea how much data was there. And you have to consider this possibility even for things essentially. Of course, for anything like coding and math, one of the things you have to understand is Project Panama basically did it mostly, actually interestingly enough, for style of good English. Because by that time they were doing this, remember they already had working models, and so they can do OCRs and they can do all this stuff very easily. So they were just trying to get better style, and printed material tends to have such style compared to like Bozo's writing on the internet. And so they were essentially trying to get it for that mostly. Okay. If you're talking about anything which has formal verifiability, such as math and code, you can generate your own data. That's what post-training is completely all about. You can generate infinite amount of data, because you have a verifier, and you can make up a coding problem, you can make up a planning problem, you can guess solutions, you can check which of them is correct. Whenever you find the correct solution, you compile that into the generator. So you're making more and more of your data. And so in some sense, that's why actually the reasoning stuff, like math and coding, we have seen the most impressive advances. Okay. Yeah.
In the video you mentioned that there were some mathematicians that came up with some new math and they kept it off the internet so that LLMs wouldn't learn.
That's just recently, yeah.
So then they tested LLMs. What did they find?
They're trying to do it right now.
Oh,
Yeah. Yeah.
because
But again, the question, of course, this whole thing is interesting. It's not like there is a separate internet. In general, putting data, so the whole business about benchmarks is completely nonsensical for LLMs. Because it's the same thing for like the fact benchmarks is kind of basically nonsensical, because the test data becomes training data eventually. And in fact, that's considered part of the thing. As I think I mentioned probably here, there was an older, like about a year or so back, there was this frontier math, benchmark. And the frontier math benchmark people essentially, then '05 came along and said, we already have a very high performance in the frontier math benchmark. Then it came out that the frontier math people generated their benchmark, and they also generated, like, quote unquote, similar problems for training. And OpenAI paid the frontier math people so that those training problems are only given to '05 and nobody else. This is basically like, you want to get, all are going, if you're taking exams, you know that Course Hero exists and the old exams are already available. So now you're going to pay to Course Hero that please don't sell your services to any of the other bozos in the class. Only I will have the access so that I do well on the exam. You see what I'm saying? Because the expectation is that the actual test will be similar to the tests that have generated before. So this is what we are going on. In general, evaluation of LLMs is very questionable, essentially. I mean, it is improving, but it's also probably because of the contamination. And that doesn't necessarily mean that the progress isn't there. Obviously, there is progress. But I'm saying objective numbers for evaluation numbers, it's not very clear. And there are all sorts of economic issues that you have heard of, basically. I mean, llama people kind of trying multiple times until they get the best answer, etc. In general, there is what's that, Goodhart's law? Not Murphy's law, which is Goodhart's law, I think, which says when a measure becomes a metric, it loses its effectiveness as a measure. Because people will find a way to beat it. Yes?
So earlier you were just talking about how if you have stuff like math where it's known and verifiable data, you can generate your own data. Since grammar and sentence structure rules are sort of like formulas for generating sentences, could you theoretically generate a whole bunch of sentence structures and then use known data to generate sentences with true facts and then
No. It's a very good question, but you are off the rails. What you will do this way is you will get good style, but not correct data, correct statements about the word. So the problem is, for Python code, there is a Python interpreter. For PDL code, there is a val interpreter. For natural language in general, there is no interpreter. Because natural language is basically making statements about the world. Whether or not those statements are right or wrong is something that basically humanity can figure out by doing experiments, etc., but there is no simple interpreter. Right? And very specific subcases such as math and code. Again, code is interesting because we are all dweebs, we are into code and we are very impressed with this. But the point about the code is not language, natural language. There is no Python interpreter for natural language. There is a Python interpreter for any damn Python program. Do you understand what I'm saying? Write any damn syntactically correct Python program and give me unit tests. I can tell you whether the code passes those tests or not. That's a powerful, powerful way to do generate tests. That's not generalizable. That's only true for Python. It's only also true for math. In math, you can have logical, lean kind of error provers, etc. Right? So it's a weird situation to even say that we no longer need symbolic anything, because we are dependent on symbolic everything where we are doing that. Our understanding of how to actually evaluate plans, how to evaluate programs, how to evaluate theorems, is what is actually coming to our aid in doing well in the coding and in the math and etc. It's a very useful approach, but it's only doable because you have that ability. And for natural language, essentially, humanity is the interpreter, quote unquote. Yeah.
For the Almo example that you mentioned for the zebra logic problems, 50% was already in the trained data, and did it perform like reasonably for the other unseen problems?
No, you should read the paper. All I'm trying to
Yeah,
say
I
is
read it.
it's not obvious to you. In fact, they found out what we were suspecting. I basically suspected this from the day one. That's why we came up with the mystery domain. Because models were improving from blocks world, unblocks world, model after model after model. But then, they were dying still on the mystery domain until the reasoning models came. And that was because I guessed that, data contamination happens. It doesn't have to be deliberate. It could be deliberate, as in the case of frontier model, a frontier math issue, but it could also be just, you're taking stuff in. There's a very interesting, weird corollary of this, which is, why did reasoning models like such as DeepSeek-R1 is the only one that we know about, right? Basically, but other people have been doing this. One of the things that they do essentially is they would generate, for the problem, they would generate these intermediate tokens before giving the solution. And those intermediate tokens, again, this is one entire thing that I talked about in my second lecture. But they tend to have some structure, and people consider that to be chains of thought, etc., etc. The interesting question is, why did that happen? And it is possible, one of the things is that it's possible that there is contamination. There's contamination of the training corpus itself, because more and more stuff on the web right now includes prompt chains of thought followed by the solution. And so any normal model that's been trained, so if you understand DeepSeek-R1, the base model should actually be able to generate, even before reasoning, quote unquote post-training, it should be able to generate intermediate tokens followed by solution. And then it generates 15 of that, let's say, and then the verifier checks if any of the solution parts are correct. If so, then it says the overall trajectory gets a point. But it had to generate this middle for even all of them, even though it's just a beginning model. And how did that happen? Because it was just basically, there's a possibility that there's enough data which got contaminated, because essentially there's, this sort of chain of thought became a popular enough area that basically there was already traces. And so that actually makes you realize that LLMs are going to be trained on traces of themselves or the other LLMs. And this has been known from the day one. And there's an entire area of research called model collapse that essentially talks about what happens if LLMs keep getting trained on themselves. Do you understand what I'm saying? So for example, one of the things is, you need more training data, right? So you take some amount of training data, you train a model, and then you make it spit out, like that guy was saying, more and more text. And then say that text is also true, I just generate and then basically make it into the part of that thing. That will be model collapse, because the stuff it is generating is not necessarily any new data from outside, it's just basically it's coming out of the LLM itself. And so, how many of you know the Norwegian seed bank? There is a seed bank, you can look up my Twitter, or you can look up Norwegian seed bank. It's somewhere in Norway there is a bank of seeds. And the idea is, in the old days, before AI, the only way the world get killed is because thermonuclear weapons. Now, of course, AI will do that. Okay, so thermonuclear weapons will kill all of us, and then all the seeds are left. Seeds are there, all the plant seeds, everything is dead. And then one or two bozos somehow survive. So they need to now restart the evolution, because the seeds are gone too. So what did they do? They essentially took all the seeds of every possible things. I hope they did enough of my favorite vegetables too, and they put them in this seed bank in the middle of some Arctic Norway. Expectation somehow is that thermonuclear weapons won't incinerate that, because there's snow, right, all that stuff. This idea, this is serious stuff. So I was back 2023 when GPT-3 became a thing. I was saying that we should take a snapshot of the current internet, put it in the Norwegian feedback. Because the rest of the stuff now is already screwed. You have no idea which is the stuff that some bozo wrote and which is the stuff these models have written. And why do you think, right, for example, every day when Anthropic, for example, said that DeepSeek people were copying their data, right? And somebody tweeted that if you ask Claude in Chinese, which company made you? It says DeepSeek. Am I surprised? No, I'm not surprised at all. Because everybody is copying everybody. The real issue is how is this going to affect the accuracy of anything? Right now, the only hope is verifiable domains for which the verifiers are outside. They are not effective.
But can that one actually like generate some plans that can trick the verifier that it's like too much true?
What does that mean?
Like since like we don't know if it's true or not, the data right now on the internet, can the LLMs generate a plan for the to trick the verifier and to say this is true?
No, what I'm saying is, basically the verifier is checking, it's basically like saying, can Python interpreter be tricked into saying that a wrong piece of Python code is actually correct on the unit test? No, because Python interpreter actually is not going to take any extra instructions saying go easy on this piece of code. Right? So essentially it takes the piece of code and it takes the unit test, it applies the test to the code, and then it basically simulates the code and then gets the answer out and then it checks the answer. That's it. That's only true because you have the verifier here. But everything else, all bets are off. Yes?
I mean, that's the weakness of the multi-agent systems that are just purely supervised by LLMs, right? Is that things can just slip through. Then you actually can trick your verifier into agreeing with something.
So if you're doing LLM to be verifier.
Yeah.
Yeah, that's a different story. LLMs to be verified. So one more thing that somebody else came out. Honestly, you can learn enough about LLMs by just reading Twitter and mute Elon Musk. That will take care of half of your problem, right? And then read AI Twitter, right? So there is a BS benchmark. BS, I'm still not allowed to say what BS is, but I know most of you know, right? BS benchmark are basically asking questions that are meaningless. Right? For example, how many milliliters of brain power would be needed to get 15 kilograms of performance on frontier math problems? That's a question. How do you know it's not a reasonable question? Right? And essentially, LLMs will answer that question. They will never say this question doesn't make sense. I mean, most of them won't, for example. And so, in fact, BS benchmark basically, this just came out yesterday. Somebody was saying that they have carefully curated. I made one up, so it's 501 now. And I hope somebody wrote it down. But 500 or so questions they made up, which basically sound reasonable, but they're nonsensical. I mean, this is basically like Lewis Carroll all over again, right? And you give it to LLMs, they will try to answer it. They will never say this is a nonsensical question. Don't waste my time. Because the problem is they've been trained to kind of please you to some extent on top of it. And again, this happens again and again and again, right? Essentially, recently, right? Somebody, day before yesterday, somebody was talking about how Claude essentially, is it Claude? Yeah, was able to, they got like the entire private data of Mexican government out of Claude. First they asked, give it to me, and say, no, I won't give it. This is what we are developing agentic systems on. And by the way, there was one other thing that happened on the Twitter, right? Which basically, this Meta woman, the woman who's supposed to be in charge of the cybersecurity for Meta or something, essentially used the agentic system, which and then was trying to clean up her mail, and it just cleaned it up. Like, shoo. Am I surprised? Like, remember that joke that, that I keep telling people that, this, like, you go to the LLM doctor and it says, yes, you're done with your left kidney, now can you remove it? And he said, like, for ingrown toenail, and this is, oh, sorry, let me try it. The question is, how costly is this, let me try it? Right now, the percentage of, accuracy, the accuracy guarantees will become more and more important depending on how costly the failure is. Essentially, yes.
This is for the point you said earlier about the test data eventually. Yeah, the test data eventually becoming part of the training data. I understand like there's a difference in learning between like you have like let's say you do the course hero technique and you study for exam that way, and like actual learning for humans. So how would you like verbalize like what's it, because for like teaching math for example, you'll be given like example problems like this is how you do this certain thing, and then you're tested on it. I understand the problems can be different. So sorry, this is a bad way of asking the question.
So first of all, I think generally be very careful about making connections with how humans learn, which we don't know how they do, and LLMs learn, which we don't know how they do. And so we're kind of taking two pieces that we equally are clueless about, and people make nice, interesting connections, and you should try to avoid that. Okay, it's essentially they just take all sorts of data and then train using this network prediction format. That's it. And is that what humans do? No, of course not. But do we know what they do? We have no idea. Okay. And eventually we'll probably figure out what LLMs are doing faster than what humans are doing because of these pesky rules that stop me from doing careful experiments on your grades. We used to be able to do that during the time of Nazis, etc. So the science, the progress of science has really slowed down because there's no easy way of doing these experiments. But for LLMs, we can do it. So we might learn what's happening in LLMs faster than we might about how humans do it, because we still have to go in this very complex route. Yeah.
I have a question. It might be a little relevant to what you asked, but can we make LLMs ground themselves on provide some sort of accents to LLMs and then have them ground on those accents and then build on top of that?
This is what's been called the constitution method of Anthropic, but it can just, it's not like this woman, Meta woman didn't tell Claude, please don't remove without checking. He said, sure. And I removed everything. And then said, why did you do it? Oh, mistake. So the constitution, it's becoming like our constitution right now. In the sense, we screw it up, and then until Supreme Court says you screw it up, we still continue. Right? So normal constitution is supposed to be that you don't get to violate it. Okay. Yeah, you can give it, but how do you know that it's actually followed? That's the part. Again, it's not that it's zero. It's not that it's completely uncorrelated. It's that there is no 100% guarantee, and there is no quantifiable guarantee as to when it will fail and it won't fail. And again, I keep saying that it's not that we didn't build bridges before we understood strength of materials. We built large, big bridges. Some of them used to fall off, and we don't hear about them because they fell off. Right? People who were on the bridge also went into the water. Well, it's okay for them. Okay. The thing that is different is with the strength of materials, we have learned to provide guarantees that the bridge that you build isn't going to just randomly collapse. So much so that collapse of a bridge is a huge, big thing. Right? It's not supposed to happen. That's the whole point of science, of strength of materials. Engineering of it basically preceded before we understood the strength of materials. And currently we are in the humongous engineering phase for the materials. And they're doing well in some cases, and in many, many cases, but we can't still do. I mean, large number of bridges are still hanging around from Roman times. But that's the classic survivor bias. Those are the bridges that survived. The other bridges went away. And the people on those bridges went away too. And that never made any big deal. People assume that bridges are here today, gone tomorrow. But what we do in this current day and age is, you build a bridge, it's supposed to stay. Because we have a lot more understanding about how to provide guarantees about, that's the whole point of science. Right? And they both go hand in hand. You do need to build bridges, and if you waited until strength of materials was understood before building bridges, then that would be a very different trajectory of humanity than the one that we actually witnessed. Right? Any other questions? Okay, let's take a 15-minute break, and then I will shift to the temporal planning. Okay, so this was the paper I was mentioning on sort of doing the verifier, training the verifier separately from the generator, and then showing that way their performance can improve. So this basically I was mentioning that's a paper. Yeah. Okay, and there was this other one that I was mentioning, somebody was asking too. Why is this? Yeah, this one actually is taking a large number of sequence plans and think of them as vectors, sentences, in terms of the actions, and then doing word vector representation, and then doing something like a sequence model. There are many, many different sequence models. These are 2016 paper. That's the journal version. Those are the two papers I mentioned. Yeah, if you want to do, I was telling you this difference between Soleimani mask, which has many, many pillars. So the free space essentially inside is split into pillars, because the pillars have to hold up the dome. And Soleimani mask, that's a blue mask, and the Soleimani mask in Istanbul, by that time they figured out how to actually reduce the number of pillars. And Taj Mahal is sort of the end of that. It's like the climax of that, where essentially there are no pillars. It's just the whole thing outside, and so when you go inside, everybody sees the outside part, but he cared about the inside part, quote unquote, supposedly. And so the inside, it's like free space, and that requires really significantly better engineering, just to make sure that things will stay in place, sort of a thing. So, yeah, so that's the basis for those things. This is from Istanbul. Okay. Yeah. So like I said, as of, I checked in the afternoon, 38 views on the lecture 1 and 26 views on the lecture 2. And the views, the so-called views, are sometimes 2 minutes and 26 minutes, etc. It was 56-minute lecture. So, you don't get it, you don't get it. It's up to you, right? I mean, that's you are supposed to make sure that you understand. You pay attention. Okay. Yeah, this is grades anyway. Okay, so I'm just going to talk a bit about temporal planning. And metric temporal planning essentially is from classical planning, go to this idea called temporal planning, and in fact also called metric temporal planning. They're like two different parts. So in the classical planning, actions don't have durations. There's also no metric quantities. In general, one metric quantity is time itself. Like the other is things like I need 5 gallons of gas, because the gas will slowly come down while I'm flying, and so I need like 500 gallons of gas, etc. So the plan has to take care of those things too, essentially. How much fuel has to be put in the plane, all that stuff. Okay, so the metric temporal planning, the special cases are just temporal planning where the only thing that changes is actions have durations and everything else remains the same. Resource planning where essentially you start talking about like continuous resources, things like fuel quantity, etc. And we sort of talk about all of them together. Again, it's a whole large area, but it is worthwhile understanding what changes when you come into this, because many planning problems are like this. Now, the interesting question is if you're looking for projects, for example, honestly, figuring out how good are LLMs for temporal planning and metric temporal planning is pretty largely uncharted area. Right? I mean, because we did it for the classical planning stuff we done. But, basically figuring out what are good benchmarks and how to actually check how good they are, etc., is going to be very interesting. And again, doing some of the same things, such as mystery domain sort of a thing, so that it just doesn't, regurgitate something that it already has. That's also useful. Anyway, that's just an idea. You ultimately decide what your projects are. Okay. So, okay. So let's look at some of the issues with time. Just basically duration of the action. By the way, if I forget, if you came, if you came after the attendance was taken and you were in the class, remind me and make sure that when you leave that your name is marked. Okay. So there are two types of things that time, kind of complain. Basically, I'm just building on top of your understanding of classical planning. So in fact, you can actually talk about temporal planning with plan space planning ideas, progression ideas, and regression ideas. Okay, and in fact, one of the things that would be interesting is that the progression, the plan space planning is the most easily generalizable to temporal planning. And it's not so much for the progression and regression. And in fact, progression was generalized, but it also winds up having some issues the way it is generalized. That's not quite understanding. Okay. Anyway, so the changes brought by the time in the planning can be grouped into two types. One is, first of all, you have clock time. And that means that you need to essentially meet somebody at 2 o'clock. And so if you come up, the class starts at 1:30. So you come at 1:45, the pop quiz is already over. Right? And this is basically, you have to plan not to be just present in the class, but present in the class by a particular deadline. Right? So that's like a metric time. And because we all need to have, so this is actually there was a caveman cartoon that was saw where this guy comes home and the other guy says, you came late, you're late. He says, no, I'm not. He says, you're late. He says, no, I'm not. And he says, prove it. So how do you prove? What is the clock? There was no clock, so you can't tell actually when you're supposed to be. So metric time actually makes it possible to talk about whether you're late or not. And then that basically with respect to which you can specify events. And one of the other interesting things is that if you want to talk about, because you have a clock, you can have all sorts of interesting things like exogenous events. That exogenous essentially means one of the interesting things we haven't talked about until now is you can make a plan that depends on something that will happen at a certain point of time and uses it to make the plan work. How many of you are thinking of Back to the Future, the climax scene? Have you seen Back to the Future? The entire Back to the Future climax scene makes sense only because this guy happens to know that at a particular specific point of time there will be a lightning striking. And so he makes his plan such that the lightning will strike and it will basically power up the, I'm giving up the, I'm spoiling the Back to the Future for you guys. So if you haven't seen it for the last 40 years or so, but anyway, so that's basically, so if you happen to know that it's going to happen, and in fact, I mean, in the case of Back to the Future, of course, it was a weird thing because he's already reliving this. But one of the advantages of entire space travel, etc., is basically you can make things happen such that you can calculate things where certain planets will be in certain alignment, etc., and you can use that to get an extra gravitational boost just by having your rocket go to that place at that time. Right? And it's all because there's a metric time. You can actually talk about. And then changes brought about by the durations to action. This is actually more fundamental to some extent. And they're kind of orthogonal. You can have actions that are instantaneous, but there is a clock. And you can also have actions that are also they are durative. Okay, durative basically means that you can have preconditions required at any point of time in the action, and effects can happen at any point of time in the action, for example. Okay, so without metric time, plan is just a beginning and end point. Metric time allows us to talk about all the time points during the execution of the plan. So that can allow you to talk about exogenous events. In particular, you can have timed initial literals, where as part of the initial state, you can say that at 0 time, these things are possible, true, and at 17 time, this will become true. At 19 time, this will become true. Where these numbers are time numbers. Okay, those are exogenous events. And so that's part of the initial knowledge itself. Like even before the plan started, that guy knew that there's going to be a lightning strike at 12:01 or something. And so that's part of the time initial difference, initial state itself. Okay? Then you can also have deadline goals. Because you have time, you can have deadline goals, metric time. So we can state that the different goals need to be made true by different deadline times. It's not necessary that all the goals have to be, the classical planning, you just say that the goals are all true by the end of the plan, that's it. But you can say that I need this thing to be done by this time, this thing to be done by this time, and you can actually say by what time any of the goals have to be satisfied. Time. Okay, that's the thing that you get to say. Again, one of the interesting things is, in a weird way, temporal planning is more known to you. That's your life. You don't do classical planning in life, you do temporal planning in life. At least you're dealing with temporal plans, because everything you do, your actions have durations, and there's a metric clock time. And so this should not be surprising to you. It's surprising that you thought the other thing is complicated enough planning. It obviously wasn't. This one is more complicated for sure. Okay, and you can also have durative goals. You can state that a certain fluent must have a specific value over an entire interval. Right? Basically, I can say, again, one of the things is, like, for example, I have to be holding the table, and let's say if you're trying to lift this table, and I'm holding this table on one side, you come holding the table on the side, and then both of us have to be holding it for the entire time. If one of us stop holding it, then the thing will fall. Yes?
If you had an action like buying eggs from the grocery store, and after 2 weeks they expire, so like whatever is true is now false after a certain amount of time, where would that lie in?
So that is basically called a process that the eggs being expired. There are two possible ways. One is that they tell you that they expire. That becomes part of the timed initial intervals. Okay.
What is it called again?
It's like initial state and the specific name. So initial state would tell you what is true at the beginning of the plan. Now it can also tell you what you know will become true at a certain point in time. Like for example, at the initial state itself, you know that at 12:01 a.m. a lightning will strike. Or June 26th, these eggs will expire, something like that.
Does it work even if it's relative to a different event? Like
Yes, again, you're asking all the right questions, but these are more into the models. I mean, we will talk about specific period 2.1 models and what they will actually allow you to say. But it's also, again, the general temporal planning is already a lot more complicated than classical planning, right? And so you have to ask all these kinds of questions. And interestingly, not too many people work in this area because it's too hard. Right, so even we used to have papers. I'll talk about stuff on temporal planning, but we absolutely won't do it right now. It's so much easier to just ask LLM something and then write papers. Right? Anyway, so deadline goals and durative goals, those are all possible. Okay. So as I said, if you have actions, right, basically because actions have durative actions, if it is a point, the preconditions have to be true before the point and effects will be true after the point. But if it's like a durative action, that means like a duration, it takes an amount of time, right, then you can say preconditions might be needed at a certain point in the time during the action. And the effects can come both in the middle as well as at the end. And one of the other interesting things is the preconditions might be needed at a certain point versus it might be needed over the entire action. And so that would be a durative precondition. That's like a durative goal. You see what I'm saying? I mean, so actions can have that. Durative actions might be, the durations of actions might be the static or dynamic. And static basically means you know that this action will take exactly 15 units of time. Dynamic means it takes 15 units plus some Gaussian noise. Okay, or for example, it takes, or the length depends on the arguments that you give to the action, for example. So, this action is to maybe like pour water or something, and depending on the amount of water you have to pour, the total amount of the action, the time that total action takes will change. Okay, and then you can even have uncertain durations. This is, even though I'm talking about deterministic side, you can have uncertainty. If you start thinking about uncertainty, you can have uncertainty in the duration itself. Okay. With instantaneous action has just before and after. Preconditions before and effects will always hold after. But durative actions, you not only have before and after, you also have during. Okay. So when are the preconditions needed? You have to explain. You have to say whether they're needed at a single point or over a duration. Okay, and that's why basically, and then when are the effects given? Are they point effects? Are they durative effects? Sometimes the effects can also be durative effects. That means that over the entire action, this particular literal will be true. Do you see what I'm saying? So because the actions have durations, they can have multiple effects on a single fluid at different times. This is a tricky point to understand. Basically what we are saying is, I'm going to remove that stuff. I'll do my best and see if this, they do have this, maybe it will work. So what I'm saying is, you have an action like this. Here it might say E. Here it might say not E, and here it might say E. Do you see what I'm saying? That there are three different. It's changing. It's flipping during the action itself. The fluid's value is changing. Right? Okay, so that's worthwhile understanding, and then they can have multiple effects on a single fluent different times. The action can make the fluent be true at the start, false after 10 seconds, true again after another 10 seconds, etc. A default assumption is to say that all preconditions are needed at the beginning and must hold during the entire action's duration, and that all effects will be available at the end of the action. That would be the default assumption. That's not required. If that is the assumption, then if in that particular case, a curative action, if you compress it into a single point, then it will be consistent with the normal classical planning, because the preconditions are true before the point and effects will be true after. Okay? Okay. The other interesting question is, with durative actions, you have this notion of concurrency. Okay, now with the point actions, it was never really clear. In fact, in graph plan, one of the things that I didn't harp on much because that's not really a defendable point, but people have looked at it that way. You know, in graph plan, basically, you know, a valid subgraph of the graph plan planning graph might well look like A1, A2, followed by A3, A4, A5, followed by A7, followed by A9. What that basically means is that you can do A1 and A2 in any order, and then they both should be done before A3, A4, A5, which can be done in any order, followed by A7, followed by A9. Right? So you could actually say that these are being done concurrently. But they really are serially done. All the parallelism basically means that you should do it in any order. You know, when you say A1 and A2 are parallel, that means you can do them in any order. Right? Serialized, they can be serialized in any order, A1, A2 or A2, A1. But then both of these have to come before any of these. Right? The true concurrency means these two actions must be done at the same time. You understand what I'm saying? So in fact, the classic case of concurrency is, if I'm holding this, you know, if there's me holding the action, hold the left side is an action, hold the right side is an action. They're not parallel, they're concurrent. And this is for this thing to actually come up, I need to hold both sides. I mean, you need to be holding one side, I need to be holding one side, and both of them should have a concurrent overlap. During that time, the table would actually be lifted. Do you understand what I'm saying? Okay. Basically, concurrency is more than just a shorthand for any possible serialization, which it is for classical planning. In classical planning, 2 points are parallel, then there is no notion of 2 points being done at the same time, because it's instantaneous. How can you have 2 instantaneous things being done at the same time? Okay, they can be done in each other. Whereas once you come to durative actions, you can actually talk about the fact that the durations of these actions must overlap. Okay, one of the very interesting questions actually about intervals in general, because that's connected, I think it's probably coming up when we see, is interval algebra. Okay, so if you have 2 points, what are the possible relations between the 2 points? This is P1, this is P2. No, P1 is before P2, P2 is before P1. They are not related. That means P1 parallel to P2. That means that either order will be fine. If on the other hand, you have interval I1, interval I2, what are all the relations between them? lot more. You know how many there are? There are 13. And in fact, there is a CSCA paper, this is called Allen interval algebra. Allen interval algebra. Because of the reason it becomes 13 is easy once I tell you the pattern. So I can, for example, start saying I1 must come before I2. I1 must come immediately before I2. That means they meet. Right? Here there is a slack. Here they meet. One second. I1 must occur during I2. Right? I1 must occur during I2. And for each of these, there's opposite one too, right? If I1 must come before I2, I2 can come before I1. That's a different thing. Similarly, I1 meets I2, I2 meets I1. And I1 contains I2, I2 contains I1. So already 6 variations. Do you see what I'm saying? So basically, you have about total of 13 variations, 13 possible relations of intervals. So for example, one of the other ones is I1 and I2 are exactly equal. That's the only one where it's both sides the same. That's why 13. You see what I'm saying? Okay, figure out the rest. Okay, but the interesting thing is intervals. This is all common sense. You do this. You're not surprised that some interval should be like, like for example, your courses, that the duration of your course must be within the duration of your program. Right? You can't say I'm done with my degree and then I'm doing the course. Then it's not part of the degree. Right? If one course is a prerequisite for other course, then the duration of that course should come before the duration of the other course. In general, courses typically don't have must meet requirement for the courses. Okay, so the other ones, for example, is ends and begins. I1 ends I2. That means they both end at the same time. Or begins. So those are all the interval relations. Okay, there are 13 interval relations. So interestingly, there's a lot more, things that you can say about interval relations. Okay, actually, the weird thing is there is a cottage industry of people in NLP who try to ask. Actually, in the second part of the lecture on the LLMs thing, I mentioned CodeTemp for the 2 hours. One or two of you who heard the entire set of lectures, both of them. I mentioned a CodeTemp database where we use that also to talk about the value that the intermediate tokens don't have to have in the video. And the CodeTemp database essentially is a temporal database with durations. So for example, who was the president of USA during 1951-52? That's a question. Because president is a durative fact. And I'm giving you a particular duration, 1951-52. And in a weird sense, actually, depending on the way I pick the duration, there can be more than one president during the duration. Okay? So people basically, for example, want to ask whether LLMs can do reasoning with intervals. And so they'll ask these kinds of questions. I mean, for everything that you learn in other courses, you can write a separate LLM paper. saying, can LLMs do whatever I learned in course 5, lecture 7? That's a good one. Right? Because you're trying to see whether because they're general purpose, supposedly, so can they do it? And if you are the first guy to ask, then we are able to do it. For class projects, these are completely fine. Because obviously you will find for unit papers separately, so why not class? Okay. Anyway, so the other interesting thing about durations is, because of durations, there is this very interesting idea about temporal plans called make span. It's a lovely name. It actually comes from the scheduling community, operations research community. The make span is the total amount of time from the beginning to the end, from the point where any of the actions start to the point where all the actions would have ended. Do you understand what I'm saying? Now, interestingly, if I tell you that an action, that I have a plan P that contains actions A1 to A10, and each of these actions have durations D1 to D10, then the interesting question is, what is the make span? Turns out it's not guaranteed. You don't know right away, right? Because it depends on how are the actions stacked. Do you understand what I'm saying? So, for example, the make span can be greater than, make span can be, it's for sure the following. Make span will have to be greater than maximum of the durations, right? Because even if you put everything together as concurrently as possible, the minimum beginning to end would be the longest action. Everything else is happening at the same time. Do you understand what I'm saying? Right? Again, make span is a very important thing. I mean, there's like, when somebody suddenly says that I need, I think there was a time, right? Basically, like, I don't know why I thought about it, but when 405 in Los Angeles, for a couple of years back, they had to do some repairs or something, and it's one of the arterial highways of Los Angeles. And so they essentially said to the contractor, this is the maximum. So basically, the contractor says these many days. So you're going to stop the traffic for those many days, because that you can't use. And then to incentivize them for completing the repairs, the innovations faster, they basically said, for every hour before the deadline, you get this much extra money. And the smart contractors basically know that they can hire more people and speed up. And if the cost that they're paying for the labor is much lower than the extra money they're making, they make it money. So actually, it turned out that it was like a kind of a scandal, because they got done like almost 25% ahead of the time. And they became really, really rich. Maybe they had some friends of theirs who made this contract for them. But it's good, right? Because I can get done faster if I pour more, put more things, put more, parallelism. And if you get parallelism, you will have more people doing work at the same time. Okay. So anyway, make span, it has to be greater than maximum D1 to D10, and it can be, if it is greater than sum of D1 to D10, then if it's greater than sum of D1 to D10, actually if it's equal to sum of D1 to D10, then it's basically that could happen when each action ends the other action. I mean, one action ends, then the next action starts, then next action, etc. And it can even be greater than that, because one action ends, and after 15 minutes the second action starts, after 95 minutes the third action starts, after 39 minutes the fourth action starts. Those are called the slack times. Do you see what I'm saying? And the slack times are your connection times in your flights. Like the first flight gets to Minneapolis, and the second flight doesn't right away start. That's what you hope, to keep your overall flight time short. But on the other hand, you also know that because of the uncertainty of connections, etc., too short a connection means that you will miss the flight, in which case you get screwed. You basically, instead of getting there fast, you get there 3 days late, because you now are no longer in your correct flight. You see what I'm saying? Okay, so the buffer times are the slack times. And one of the interesting things is, if there are buffers, then you can condense. You can push things, to reduce the buffer and make it essentially the make span is smaller if required in some cases. Okay, and if make span is less than sum of D1 to D10, then there must be concurrency. You see what I'm saying? This is basically pigeonhole principle. If it is less than D, you guys, by the way, do you know pigeonhole principle? Okay, so if it's less than D1 to D10, sum of D1 to D10, that means there must be at least a pair of actions that are overlapping in time. Okay, now the interesting question about this concurrency, so this is what it's completing this, actions don't need to start right after the preceding action, and then planned idle slack time may not always be a bad thing. It can sometimes improve the robustness of the plan. That's basically the difference between, short versus long connection times, right? Basically some of us, for example, my wife would like to have a decent 3 to 4 hour connection time, especially in international flights. And I actually went to India this time on Cathay Pacific, 1 hour connection time in Hong Kong. Pretty much anywhere else, no other US airline would have even considered, a flight which has 1 hour connection time, because it takes 1 hour to just get out of the damn plane, right? But in Hong Kong, they knew what they were doing. They will essentially, everything works, and then you will basically add extra time within the 1 hour, right? Essentially, because part of it is also that the planes for the international flights, basically, depending on the air, depending on the wind push, etc., that the actual time of arrival is basically faster than what they advertise. Right? Anyway, so planned slack time is the way you improve the robustness. Having long connection times makes sure that you have a better chance that you will actually reach the thing without missing a connection. The expectation is once you miss the connection, then you have to replan, and that'll be a much worse situation. Okay. So again, plan 1 schedules 5 minutes for connection time, plan 2 schedules 1 hour, plan 3 schedules 2 days. Which one is better, all else being equal? That's your quality preference to some extent. Obviously, if you think in terms of make span, obviously one is not better than the other. But the only reason one of them is better than the other, different people find different things to be better, is because they have more of a downside for missing flights. And if you miss that, and in fact, did I mention this thing that somebody actually said, this OpenAI person was saying that if you don't miss 1 out of 11 flights, then you are not, using your time well. So those are people who are like the opposite of my wife. So they're essentially basically saying that if you're having too much buffer time, then you're hanging around doing nothing in the airport, instead of selling your services to somebody else. So the more of a buffer time means that you won't miss the flight, but you also have less time for other things. Yes, you have a question.
Regarding the make span, so you say if the make span is the sum of the durations of each action, then it is a strictly serial plan. But if there is idle time and concurrency, it's possible that
yeah, you're right. You're right. So basically, I think what you were saying is this is the one that is actually, you should consider the slack times. If some of this thing and there is no slack time,
yeah,
then it is strictly serial.
yeah.
Okay. Yes.
Is robustness only relevant in a non-deterministic system? Because if something is deterministic,
Yes.
then
You're right.
we haven't started non-deterministic stuff.
You agree. But what I'm saying is everything is connected to everything, right? So,
Sure.
so the point is, the reason we have buffers at all is because we believe that connections will fail. If connections will work as advertised, right? And what the airlines are doing is that they are considering, 90% of people will make the connection, other people will fail, and that's fine, we'll just put them in some other thing. So, but if you're one of the people who miss the flight, and if it makes a big difference for you, then you will wind up having longer function. So the only reason to make sense of slack in the schedules is because of robustness. Otherwise, why? Right? Okay. But notice the kind of discussion we are having right now, which is all about planning, and it makes complete sense to you, and yet you didn't miss it when I was talking about classical planning. You thought that was fine too. But actually, this is more like the kind of plans that we care about. And then resources, actions might produce as well as consume resources. The main consequence is that we have numeric state variables. State variables used to be true and false before. Now you can have state variables that are essentially metric, they're real numbers. And then, an action can increase or decrease. Or it can also kind of make a continuous change over it. Do you understand what I'm saying? So all of a sudden now this becomes closer to things like real world-ish planning. So, one of the things people who are like very much into this whole temporal planning is the NASA people. Like, essentially NASA has one of the best planning groups, and then they have to, because basically real world planning essentially is durative. And you have to consider resources, the things like fuel, etc. All that stuff is part of the issue. Okay. And then actions can update a numeric state variable just as they assign a non-numeric one. So resource quantity after action is equal to some function of resource quantity before action and the action parameters, essentially. Updates can be either linear or non-linear. You can also kind of do discrete updates saying, resource would be added 5 gallons or something like that. So now this all brings up the issue of how to handle this, quantities, durative actions as well as these resources. Okay. So there is a standard called PDL 2.1, and this is actually bringing you to the next homework, which is basically just like you did the PDL 2, for which you wrote a couple of domains. You will now write some temporal domains just to get a sense of how to write. And any standard gives some, it models some things and not others. Okay. So PDL 2.1 allows durations that allow static as well as dynamic durations. It also allows duration inequalities. And then it has preconditions are only going to be allowed this way, at start or overall. Those are the only 2 types of preconditions. Even though you had things like middle preconditions, they don't model that. Okay? And fx can be at start or at end. Okay? And then the numeric quantities can be present in the preconditions or fx. Presence in the fx can be discrete. And continuous change can be specified by giving a rate at which the quantity will change over the duration. Okay? That's basically what PDL 2.1 standard, which basically, it has a language. Here is an example. Durative action, burn match. Duration is 15 units. And the condition is at start you must have a match. And at start you have also a strike pad. And then you strike the match on the strike pad to get the light. Effect is at start you have light, and at end you don't have light. Okay? And durative action cross seller essentially this is basically a very simple domain where you strike a match, you are trying to walk inside your basement and it's dark and no lights, and so you strike a match so you know where you're going, and then you walk and then you basically repair the fuse. That's it. Okay. But notice that here one of the interesting things about concurrency that I wanted to mention, and that actually becomes clear here, is you can do concurrency for efficiency, or you can do concurrency because it's required. Do you understand what I'm saying? Right? So if it's required means that unless you do those actions with overlapping durations, you won't get the intended effect. Versus you are doing them in overlapping durations just to reduce the next step. Do you understand what I'm saying? Okay, one is called normal. So the second type where the concurrency is, the place where the concurrency is needed to have the intended effect, that's called required concurrency. That means without the overlap, the plan cannot work. Why am I making such a big deal? It turns out that if in fact concurrency is only an efficiency hack, efficiency hack means that essentially you're just doing it so that the make span is reduced, then you can, for any domain where all problems have solutions that don't require concurrency, don't require it. They're happy to have it to kind of make it more efficient, but they don't require concurrency. Then you can, in effect, solve those problems using something like a classical planner, which will give a sequential solution. Then you post-process that sequential solution so that you kind of pack it up, cram it up such that more and more stuff is parallel. You see what I'm saying? That will reduce the mix. Okay? On the other hand, sometimes there are problems which require concurrency. And for problems which require concurrency, that means there would not have been a solution for that problem if you're only searching in the space of sequential plans. Do you get this? Which means that the earlier method would be incomplete. For any problem which requires concurrency, this idea of looking for a sequential plan and then making it more parallel won't work because it won't actually find a sequential plan. Remember, mystery domain came from planning benchmarks, right? Part of it is in planning area. We used to look at these benchmarks to kind of look at how fast planners are, etc., etc. And one of the things that we did, and I'll make you read a paper, I don't kind of time for the point of it, but I'll talk about it here too, is for a while in planning domains, there was, in planning competitions, there will be temporal planning domains, such that all those temporal planning domains, none of them required concurrency. They basically had durations, but they didn't require concurrency. So you could have actually solved them without, without a real temporal plan. I mean, you can have a sequential plan that will basically solve that thing, and then you make it more, pack it up. And at the same time, one of the planners that was actually, one of the class of planners that was actually pretty popular for temporal planning was a planners based on progression, which is actually an interesting enough idea. I'll explain in a minute. Because in trying to do progression in temporal domains, right, basically you need to consider, you start, you put an action, right? And then the next action, you can either put it at the same point or move the clock and put the action there. So there is actually a kind of a clock pointer. The clock pointer is in the beginning at the 0. And then you put an action, and then whenever the clock pointer is there, then you'll keep putting actions at that point. And then you have a separate idea called move the clock pointer, which will be moved to some, either the end of an action or some distinct point. And then you will start stacking actions there. If you do it this way, then essentially you can define a generalization of progression, which will basically define the states after actions. And this is called the temporal epoch planning, and I'll describe this to you, partly because we did one of the planners. And these planners were winning the competitions. These planners turn out they can't actually solve problems that require concurrency. But nobody noticed it because they were using benchmarks that didn't require concurrency. This is the problem with benchmark-driven research. So in a way, kind of, we are, at least people, at least I am sort of attuned to this, that any benchmark-driven research, you might think that everything is working because the limitations of the solver and the limitation of the benchmark are nicely connected, so you feel as if progress is being made. Do you understand what I'm saying? Right? If there was a, benchmark which actually wound up requiring concurrency, then you would have known that this guy is failing, and so you could have lost the competition. But because all of the benchmarks just happened to be not requiring concurrency, you never knew this. I actually mentioned something very similar to this in the context of LLM planning. Part of the reason people thought LLMs were doing planning is because they were happening to look at domains which don't have interactions. Remember that thing where you take Bloxworld and remove the preconditions and the delete things and LLMs start doing much better? So if all your benchmarks, including the tau bench, don't have any action interactions, and LLMs are actually doing well, you think LLMs are doing well because the benchmarks are doing well. But the benchmarks actually are not capturing the true extent of planning. And LLMs actually can't solve the problem. In fact, if it required, at least standard LLMs can't solve the problem if it required actual action interaction. Then you would not know. You are like ignorant on both sides, so you feel good. The reason I bring this up is, again, the required concurrency happened in temporal planning way before this stuff in LLM. So I was sort of, at least from my perspective, I was attuned to kind of looking at if there's a benchmark, what are they hiding in the benchmark? Not necessarily deliberately, but ignorantly. Anyway, that's all like a foreshadow of what we'll do maybe in the next few minutes as when we come back to the next class. But, and I'll get you to read the temporal planning paper as a required reading for the next class. So anyway, this is a very simple domain, crossing cell R, which requires concurrency. Okay, by the way, yeah, I'll get that in a minute. So it requires concurrency because the point is that you have to burn the match, and while the match is being lit, you have to cross the cellar to the other end and then fix the fuse. If the match is over here, then supposedly you can't walk because it's dark. Do you understand what I'm saying? So this is not a question of efficiency hack. You're not doing things, two actions in parallel just so that the make span will be reduced. Without those two actions in overlapping, the plan won't succeed. It's the same reason equivalent version of this is I'm lifting from left of, I'm lifting this side, you're lifting the other side. If they are not both concurrently done, this won't be lifted. You see what I'm saying? And by the way, the notion of required concurrency, as I was mentioning here, is also worthwhile to talk about for agents. And there it becomes required cooperation. Are you having more agents just to improve the speed? Are more agents needed because they must cooperate? One agent cannot do it. Do you understand what I'm saying? So you differentiate efficiency from feasibility. And then if it's not even feasible, that means it's required. If it's mainly being done for efficiency, then it's not required, but it's a useful efficiency. Anyway, so you got this sense, right? So this is how the domains will look, right? Now previously it was much simpler, precondition effect, you're done. Now precondition effect, duration, all that stuff. And so the next homework, you will write some domains in this so that you'll get a sense of this. So then you can also have durative actions in numeric quantities and discrete effects. So for example here, at start, decrease the energy by in this rate, according to this rate. Again, modeling the domain model is one thing. Having a planner that actually generates a plan for those domains is a different thing. Up until now, I'm just talking about express image issues. What can you model? Okay. So one of the interesting questions is, it's not being shown here. Yeah, so what is happening here is interesting thing that this is a modeling decision is if you're reading this, it's saying at the very start itself you are decreasing the energy. completely. So similarly, the idea would be, even though the energy is going to be reduced over the entire period in an arbitrary fashion, you could model it in such a way that the moment the action starts, as far as you are concerned, it will only end, and by the time it is ended, you would have this much less energy. So I will make that be the action upfront, the effect at upfront. So in some sense, that's a modeling approximation. There are certain things that the other one, which will show how the energy is slowly changing over the durative action, it can be used to do other things compared to this particular modeling, where you're actually saying you're going to lose all the energy you're going to lose for the overall duration in the beginning itself. You understand what I'm saying, right? Because it's actually, if it's like a 15-hour duration and then the energy is falling in an arbitrary fashion, you could basically model that. Or you can say this much energy will be gone by the end of this. And once the action is started, I can't stop it anyway. So I might as well assume that it's okay. Okay, those are the modeling issues. Okay, and then, so here this is a slightly different version where you are increasing it over the duration. Instead of saying at start and at end, you're actually showing how it is going to increase over the duration. So you're kind of giving the more continuous change. Okay, and so there are all these. By the way, you forgot to mention this. PDL 2.1 level 3 allows only this kind of modeling, and level 4 allows this continuous change too. Okay. Okay. Then basically this was like already old stuff. I'm actually not even sure where the temporal planning stuff is, but when I was paying attention quite significantly, they started with level 1 is just trips ADL that you already looked at. Level 2 is durative actions. Level 3 is plus numeric quantities. Level 4 is plus continuous change. Okay, and we are mostly going to be looking at level 2 and level 3 in this class, in these discussions. Okay. Okay, the other thing is you can compile durative actions into instantaneous ones, which is basically by saying start point, end point of an action. Right? And the action start, action end, and you can say the preconditions that are supposed to be there in the beginning of the action will be at the action starts preconditions. Preconditions that are required to be there at the end of the action will be the AE's preconditions, and then the effects at the start, effects at the end, and any preconditions that are supposed to be overall are essentially an interesting causal link, like an interval preservation condition from AS to AE. Right? It actually turns out that you can basically say with this that you can solve durative actions with plan space planning. You're done. Right? Because if you have durative actions, you basically think of each durative action as start point, end point action. Right? Then you essentially have a normal plan space planning representation. It's just that you don't have you have no choice in saying I'll put AS, I won't put AE. You put AS, you'll get AE. You put AE, you'll get AS. Right? Because they're connected. Okay? And the conditions themselves, the preconditions and the interval preservation conditions, they're already present in the plan space plan. Not surprisingly, when temporal planning originally came along, the first temporal planners were plan space planners. Do you see what I'm saying? They are because in some sense it's a no-brainer, because plan space planners already think in terms of steps and basically interval preservation constraints between steps, and and then you will have, and one of the advantages of this is actually the quote-unquote interval algebra really is nothing but interval algebra is really nothing but I1 is I1S, I1E, and I2 is nothing but I2S I to E. Right? The start and end points of the intervals. And the interval relations are how all we know is S is before E in both cases. I1S is before I1E. The question then is, how is this and this connected? How is this and this connected? How is this and this connected? And you can actually say, for example, interval meeting is I1E is the same as I2S. Do you understand what I'm saying? If I1E and I2S are at the same time, then that is basically intervals meeting. Right? So essentially, this is the interval algebra can be converted to point algebra, where each action is actually start and end points, but they are not arbitrary start and end points. Unlike classical planning, where each point is independent because each point corresponds to a different action. Here, start and end point are of the same action, so you can't take the start and not the end. But it allows you to essentially use the same exact plan space planning algorithm. Okay? Yeah. Actually, let me just show you that, how the plan space, before I get there. Just 1 second. Yeah. Yeah. So this is actually the most obvious way to do plan space planning, temporal planning, which is basically just take the plan space planning, and it works out of the box almost, essentially, because a partial plan is just a set of constraints over steps, and each action now has 2 steps: beginning step, end step, and which come together. And the constraint set is the same precedence relations, interval preservation constraints. You see what I'm saying? So it's essentially, instead of constraints with respect to steps, you now have constraints on the time points. Okay? And so you can actually do plan space planning with this representation. And so essentially, if you wanted to solve this cross-seller burn match thing, you can do plan space planning, follow the plan space planning idea in terms of open conditions and unsafe leaks. Remember, that was the flaws that we had. Okay, and the open conditions would be the goals that you need to, goals are the preconditions that you need to support. Unsafe links is any link that somebody is violating. And it includes, for example, if an overall precondition on an action and somebody else's start or end point is coming in the middle and it's killing that, that's not allowed. And it just comes out of the box. Basically, plan space planning does that for you. Okay? So it turns out that this is basically one of the oldest papers, a Zeno planner from 1994, essentially just did this. And if you read the Zeno planner paper, it's not that different from the partial order planning that you read. In fact, the tutorial on partial order planning that I made you read by Dan Bird, it was Dan Bird and his student who did Zeno. Right? So it was understood that plan space planning basically was one of these ideas that work all the time. It's just that's not very efficient. And it was basically going to deal with temporal planning. What was surprising, honestly, and I'll prepare the stage and I'll make you read and then we'll discuss in next class, is I'll get this in later, but is that how do you do yeah, so how would you wind up, okay, no, I need to get this correct. I want to show you one particular slide to get you. Give me a second. Yeah. So in fact, I have it in the right order. So plan space planning works fine. The question is, can you produce temporal plans with progression? Right? And I'll actually give you an interesting idea. That almost works. And we actually wrote that plan. And then some number of years later, we found that it actually doesn't work if concurrency is required. And so then we had to write another paper saying the entire competition was wrong because the benchmarks didn't require concurrency, the planners actually don't support concurrency, and so we are not realizing. Okay, but the idea is interesting. How do you actually do progression with, progression due to reactions? The one idea is think of progression planning with, with actually the point actions, that is instantaneous actions, but consider progression not just sequential, but I want to generate this graph plan like plans. It went away, where remember A1, A2, followed by A3, A4, A5, followed by A7, A9. I want to generate those kinds of plans directly. To do that, what you basically have to do is, the naive idea is basically, is to kind of, that one idea of doing that would be to project, instead of projecting the whole project, whole progression idea, you start from the initial state, project the state over action 1, action 2, action 3, you get the search tree. And then you again project all the actions until you reach the goal state. If you want to allow for multiple actions at each point, then you need to consider subsets of actions. So one dumb idea which will work is consider every possible subset of non-interacting actions. That means if you are non-interacting, that means doing U in parallel is well defined. Right? Similar to the graph plan non-interfering actions. So if you consider all possible subsets of non-interfering actions, right, and then you basically consider the branching over them and do progression that way, then you will get parallel plans. You realize that? But basically, it has exponentially increased the branching factor. If there are n actions, in the worst case, there will be 2 power n subsets of actions. Right? But it will work. A better idea is to essentially consider changing the search a little bit, such that you not only just lengthen, which is what progression does, but fatten and lengthen. So at any given point of time, you get to either fatten here, that means add more actions underneath, or lengthen, which is push the clock and start adding actions in the next one. And it's a search choice you have. Right? And if you do that, then essentially we start by representing the state of the partial prefix as S followed by A1 to AK, where A1 to AK are the mutually non-interfering actions that we have already committed to applying at the state S. Okay, and then you get to either add AK plus 1 to this set, it will be fattening it, or you decide to push the clock and then start adding actions the next level. Once you do that, you can't come back. A normal progression basically always only lengthens, never fattens. This one does both fattening and lengthening. You see what I'm saying? If you can understand this idea, okay, so fattening doesn't, actually the pushing the clock essentially means advancing the state. Because when you're fattening, these are all non-interfering actions. They state S1, I keep adding more and more actions in parallel. After I start adding actions, then the next state is well defined. So when the clock changes, the new state is provided. And from that state again, I get to fatten. You see what I'm saying? Okay? So if you think of progression this way, then fattening and advancing, I call it lengthening, but advancing the clock or fattening at the current level, this idea pretty much looks like it can be generalized to derivative actions. So in general, basically, what happens is, and I think that's where you get to read the paper, the part of the algorithm, and I'll discuss it in class. So you, unlike the actions here, what might happen is you may well have things like this. You have start as 0, start as 0, and you can put this here. So you have a 0 beginning, and then action A1, action A2, action A3, let's say. Right? Now I can fatten by adding action A4, assuming that none of them are interacting, or I can lengthen by advancing the clock. The only question is, if these were all points, then it's very clear how to advance. If this is S1, you advance it to the next point. But here, each of them are different lengths. Right? How do you advance? The idea is you advance to the next event. In a sense, you can't advance, for example, if you want completeness, you should definitely not advance it beyond this point. Because this is the shortest action. There may be interesting things happening at this point. Do you understand what I'm saying? So if you get that idea, then you really realize that what you will wind up doing is these actions will have interesting effects occurring at different times. And when you are advancing the clock, you advance it to the next event in the event queue. Event basically is an effect happening at that point of time. And typically they happen in the start or the end. And then when you do that, at that point, when you do that, let's say if I advance it here, then I will start adding actions here. You see what I'm saying? It looks pretty complicated enough now. It looks there is like a certain amount of concurrency here, there's a certain amount of concurrency here. This is the planner called SAPA that we actually developed. And and SAPA is anybody from Vietnam here? SAPA, SAPA. So this is Min Do was one of my early students, and so he gets to name his thing, and SAPA is, and I didn't go, unfortunately, I've been to Vietnam, but I didn't get to go to SAPA. But this is this lovely valley apparently in Vietnam, and so the planner SAPA was made based on that was named for that, and essentially it's a forward chaining heuristic metric planner. And you will read the algorithm. Basically, I gave you the idea already, and we'll discuss it again. The idea is it's fattening and advancing. Advancing is well defined if it is point actions already, because all points are aligned, so you go to the next. But if they are different durations, then you need to, at the minimum, say you can't advance it beyond the shortest action. More generally, you can't advance it beyond the next event in the event queue, where the event is every effect and the time at which that effect is going to happen. Yeah?
So the next event is decided by its duration?
No, next event is the event will basically say the condition will happen at this time point.
So that will have already.
That we have, because the moment you put in the action, you know that the action will have effect at its end. And so you put those events into the event queue. So these are stuff that you know are going to happen because you put this action in. And so you basically extend the clock up to that point. And if you do this, you will just generate these plans, and these are pretty nice plans and they work. But it turns out, as to kind of spoil the thing, that it turns out that SAPA, which actually won competitions, basically doesn't solve temporal planning problems when there is required constraints. Yeah.
Can you say an event is any change from the current state?
No, you will read the algorithm in a bit, basically I'll make you read it. But essentially, the event queue would be the moment you put an action, action will have this effect at this point. So action has well-defined start and end points. and it can have effects at the start and the effect at the end. So the start effects are already there, and the end effects are going to come when the action ends. And so there may be an effect here. And so that event is, events are basically sorted in the order of time. And the earliest event is going to be just put in. Right? Okay. Again, I just basically gave you an idea. You're going to spend some time, you're going to look at the algorithm, and we'll discuss next class. It's a nice algorithm. It looks like it actually solves lots of interesting problems, but it turns out that's the point of guarantees. You say that something is working, what is the actual proof? And so, for example, it turns out it actually solves pretty much lots of temporal planning problems unless there is required concurrency. And one might argue that if there is no required concurrency, then it's not really a temporal planning problem because you could have solved it. It's pretty much any normal planning, sequential planning, and pushed the things back in. And the reason this is all interesting is because any benchmark-driven research should be, kind of connected with understanding of principles. Otherwise, you're thinking that you're making progress, but the progress could be failed. Because, there is combined ignorance on both algorithms and the benchmarks. And with LLMs, there's no algorithm to begin with. Right, essentially. It's like at least SAPA, you know what the algorithm is. In algorithm, you did it, man, that's it. And what do you do, man? Well, my benchmark, but if you look at the benchmark, does it have like these kinds of normal characteristics that would make planning problems hard? Okay, let's stop here. Thank you. What? Yeah, what's your name? Zamad, sorry, okay. What? Ram Menon. Menon, M-E? Menon, yeah. What's your last name? Gumadi. Yeah.
I was late for the.
I agreed for you, yeah.
Shaker.
What?
Shaker.
S-E-S-H-E-K-H. S-H. Oh, S-H. Oh, this one. Okay, thanks.
When are we expected to have the midterm exam?
You will know that before the midterm.
For project, I asked if we could have any compute on Soul or something so that we can.
We are trying to do that. Yeah. I'll send message.
One of the slides mentioned the midterm. Is that posted somewhere on the schedule or?
No, I will tell when the midterm is.
Okay.
Oh, 1 second, I need to stop this.